think about what we call the control chart. Okay, control chart. And actually, for the SPC, if you want to study more, it's just like the one course, right? Not just one chapter that we study. But since we just want you to know about the basics information about the control chart, so for our class we will study just for the 4 chart from the control chart. So we study X bar chart, R chart, C chart, and P chart. Just 4, but actually it's have more than that. Okay. And also we're gonna talk about a little bit about run test. No calculation about the run test, but I need to mention about this because it's about the method that we're gonna test about the viability of the process that it's gonna have like a pattern in the control chart or not, something like that. And the last part is about the process capabilities. Right? So 2 main things, right? SPC and the process capability. This will be the 2 main things for today's topics. Okay. So let's start with the basic information about the quality assurance, right? So we know that in the concept of the quality management, we talk about the continuous improvement. Right? The continuous improvement is just like the way that we try to do in order to improve the qualities, right? Both the product and services, and also all the organization. It's just like for the long term, right? Or not just only the long term, but also it's about the way that we try to make it not using the concept of inspection, right? Because the improvement, continuous improvement is mean that you need to do since the first time, do the right things in the first time, and then you try to improve and improve again, something like that. But inspection, we talked last time, is about the way that you try to detect the defective products or the defect of the products or the services. Normally we use this before and after the production just for checking, but it doesn't add in the value or add in the quality to the products. Right? And anyway, both inspection and continuous improvement is not cover one thing that is mean during the production, right? For during our production, we have another concept that we can use for the quality assurance. It's called the process control. So for the process control, statistical process control, it means that we're going to using the statistical method to evaluate the output of the process that we interest, right, during the production, right? And we try to see that is there any variation that's come from the mistaken of the human, or the variation that's come from the procedure, operation, or machine or not, right? All the variation that is not come from the natural variation, we don't want it. Right? So the statistical process control, we try to use the statistical method to evaluate that process and see that whether or not we're going to have the variation that is not come from the natural variation. Right? But even though that we have the process that doesn't have any abnormal variation, but we still want the output is stay in the specification. So then, besides the statistical process control, we still need to test or to evaluate that whether or not the product and service from the process is conform with the specification, right? So that method we're going to use the process capability to measure. And anyway, let's starting with the SPC, right? So I'm gonna make it real quick because for the important things I will gonna give you more detail. But there's something in the slide. Maybe it's just the description, right? You can see in the textbook. So the SPC, as I mentioned, that we're gonna use the statistical method to evaluate the output of the process, right? And the objective of the SPC is try to detect whether or not we have the abnormal variation or non-natural variation, right? So we call it assignable variation. Right? So the SPC much more relying on using the apply of the control chart. Right? So it means that for this chapter, we need to develop the control chart, right, to evaluate the process. Okay. And as I told you that the variability is actually in every process, we always have the variabilities or variation, right? There are two types of variation: natural or common, right? Variation or common cause, and special or assignable variation. Right? Sometimes we call it abnormal variation. Right? So the first one, natural or common, this is the variation or the variability that always exists in every process. We cannot delete it, right? We cannot eliminate it, right? It's still there, right? But we okay with that because the variation that comes from the natural cause is just very little effect, right? But the variation that come from the one that we call the special or assignable variation, this is the one that is abnormal because it's come from the mistake of the worker, it's come from the setting up of the machine, it's come from the procedure of the operation that is not correct, something like that. So we can delete it, we can eliminate it. So that's why we don't want this violation, right, occur in our process, right? We want to eliminate it. And SPC or control chart is about the method that we can use to detect, right, that whether or not our process have the assignable variation. Right? And generally, if the process has just only natural variation, the output of the process can be like the random output, right? Random output. But if you have like the natural variation occur in the process, the output is going to have something that we call like a pattern or something that is not that normal, right? It's true like maybe you have like a pattern of trend or you have like a pattern of bias. I will talk about this later. Okay, and some people curious that why we need to use a control chart, not using the histogram. We already talked about histogram. This is a tool again that we use to measure about the dispersion or variation, right? But it's different from the control chart because the histogram cannot measure the control chart, cannot measure the output of the process over the time, but the control chart is can, right? So then when we try to plot the control chart, we plot against time, right? We against the time, right? Sample from each time, normally every hour or something like that. But for the histogram, we cannot do that. So that's why we need the control chart to evaluate the process because it can take account of changing over the time. Okay. And for the step, right? We're gonna start with the setting up the control chart, right? And then use that control chart to monitor and evaluate the process, whether or not we have the assignable variation. If you don't have any assignable variation, we have only the natural variation, we call that process in control. And we're happy with that. But if you have the assignable variation occur in the process, we call that process is out of control. So then the process after that, we try to go more detail to investigate why do we have that variation, and we will find the reason, we will find the answer, we will find the cause of that variation, and then we try to eliminate it. Once we eliminate it, then we construct the control chart to test the process again to make sure that we don't have any assignable variation in the process. And then the last one is that once you have the process, it stay in control. We will need the process capability to make sure that the output of the process is stay in the specification or not, right? By using the calculation of the process capabilities, right? And I will talk about this in the last part of today. So, in conclusion, this means that we prefer process in control, and process have to be capable to produce the output within the design specification. So this is what we prefer. We prefer process in control. It's been no assignable variation, and we also prefer the process produce the output, right? Capable to produce the output within the design specification that the customer wants. And this is the flow chart that just I mentioned to you that we're gonna construct the control chart and see that whether or not it has the assignable variation or assignable cost, right? And if you have it, you stop the process and then you find out why. Right? And the concept of the developing the control chart, we're using the concept of the sampling, right? From the output of the process. Right. We do the sampling, and then we're gonna have the formula to calculate what we call the control limit, and then we're gonna construct the control chart. Right. I will show you in the next few slides. Right. So this is just the process. Once again, define is what? Define means that you try to select the process that you interest. Right. Normally, it's about the very critical or very important process. Right. And then you do the control chart to evaluate it, right? So measure is mean since we have several types of the control chart, it depends on what kind of the data of your output, right? So if sometimes your output of the process is just the time or the dimension or just those kind of things. It's like the continuous value. So we're gonna have the set of control chart to measure. But if you have the output of the process, it's not that continuous value. It's just like the category that, okay, you have scrap or non-scrap, you have like a defect or doesn't have the defect, something like that, right? Or like the category, right? We're gonna have another set of the control chart to measure. Right? So it depends on the type of the data. I will talk about this in the next few slides as well, right? Again, we compare with the control limit and evaluate that whether or not the process is in control. And then if you have the assignable variation, we try to eliminate it or correct it. And then we reconstruct control chart again to monitors. Right? So this is just the one that I will show you more detail, right? So you need to determine in the real world, you need to determine that, okay, which process are you going to measure, right? And what kind of the sample size that you're going to sampling from the output of the process. You're going to record the data to plotting, right? The statistic on chart. Right? Normally it's about the average value. We're going to do like the calculation of the control limit, right? And we analyze that it's in or out of control. If out of control, we eliminate. Right? We try to find the cause of that variation and try to eliminate it. So don't worry, this is just the framework, right? I will go into more detail than this for the calculation, right? And then the last one is that we try to check that the process is capable or not that produce the output within the design specification. Okay, so before we go to more calculation, right? Detail about calculation. Once again, this is like a detail that's quite important. As I mentioned that we have two types of variation, natural or common variation, right? This is just like the variation that already exists in every process, right? We cannot eliminate it, right? As I mentioned, right? And if we have the process that have only the natural variation, we call that process in control. But for the unassignable variation, right? This is the one that we don't want it, right? So the objective of the control chart is to detect whether or not our process has this assignable variation. We need to eliminate it, right? Because this is come from the mistake that not normal way, right? And from the next slide, right, I will starting with the concept of the control chart. So as I mentioned that the control chart is developed by using the concept of random sampling from the output of the process. So you need to understand this kind of thing, right? So I'm going to use the example of the process that produce the output of the boxes of cereal, right? And for sure that let's say that you have a box of cereals. The thing that you're going to serious about is body weight. So every box needs to have the same weight. Let's say that 500 grams, you have to have like that 500 grams for every box that they produce from the process. So let's say that for the first hour, I'm going to the production line, and then I random, right, sampling 5 boxes of cereal from the production line, and I measure the weight every box, and calculate the average weight. So the value that I get, I record. So one box that shown here is represented for average weight from 5 boxes that you sampling from the production line. For the second hour, I'm going to the production line again, sampling 5 boxes, measure the weight every box, calculate the average weight of 5 boxes, and then I'll record. I'm doing just like this every hour. For sure that there is no way that we're going to have the same weight, same average weight for every hour, right? We're going to have like a variation. So maybe this box this one is maybe 500 grams. This one is 500.02 grams, something like that, whatever. So we're going to have there some variation. And if I try to do this way for every hour, again and again and again, I'll record. So finally, I can see something like the distribution of the average weight from 5 boxes that I'm sampling from the production line, right? So if I'm drawing the solid line from that record, I can have the graph, right, that we call the sampling distribution, right, of the weight for the box of cereal, right? And for sure that for our either we want it to be the normal distribution, just like this, okay? And in the real ones, maybe it's not normal. This can maybe you have like the other distribution that's going to left side, right side, something like that. But right now, let's say that ISO is normal. First, let's say that ISO is normal. But for this one, once again, wheel shape or the normal is either that we want, right? But actually, maybe it's not. Maybe it's shift, right, from the central. Maybe it's the variations. We go to more variation or less variation, or you go to the left side or right hand side shape, whatsoever, right, that I mentioned. But if we have this one, let's say that I'm going to go to. I'm sorry that I'm one mistake for me. Sorry. Repeat again. One mistake for me. For the first hour, I'm sampling 5 boxes from the production line. I'm record the average weight from 5 boxes and go back to that production line again. I'm doing again and again. So I'm gonna have the distribution for the first hour. Okay, not too many hours as I mentioned. If I do something like this, right? This is the graph of distribution for the first hour. If we do it for the second hour, I have this distribution. For the third hour, I have this distribution. The fourth one, I have this distribution. So it's like the same, right? So if I ask you that, okay, what you expect or prediction for the distribution for number 5, should be the same. So in this case, this kind of thing here, we call it in control. Why in control? Because we can predict the output. That it's going to be the same, right? It means just like this. There is nothing wrong. There is nothing that different. But if you do the way, as I mentioned, that you try to develop the sampling, this is for your first hour, this is for your second hour, this is for the third one, this is the fourth one. How about the fifth one for duplicate? We don't know. Since the first 4 doesn't the same, this is difference, right? So this thing we call is like the out control. Okay. So in this case, right, this kind of meaning of the in or out control. Because if you have the process in control, it means that you can make sure that the output of your process, you can predict it that it's going to have the same distribution from time to time. The same. But for our control, you cannot predict. The distribution from the sampling might be different. We have no idea what's going to be the next one or the next 2 hours. Okay? But anyway, the one that I just showed you we develop from make the sampling of the production line, right? That sampling we call sampling distribution. But if I not make the sampling from the production line, but I use all the output to record the weight and develop the distribution, that distribution we call the process distribution. But we cannot do this in the real world, right? Because when you make the production line, you have a lot of output. It doesn't make sense that you take all the output to measure the weight and develop the distribution, but you just make the sampling of them. So we do the sampling distribution, not the process distribution. But we can use the sampling distribution represent for the process distribution. Okay, and this is not the same, but it's quite different. For sure, the process is quite more variation because we have a lot of output. But based on the concept of, you may study the stat already, is central limit theorem. We assume that if you make the sampling well, a lot, that enough, no matter what your population or distribution of the process is, what kind of distribution that you have, the sampling distribution is going to be normal distribution, that you have the same mean, right, of the process distribution. And this kind of detail I'll show you later. So this normal distribution, we know that. At the center is mean. And normally for the base of the distribution, we measure about the dispersion using the standard deviation, right? So if you go from the center, both sides, to standard deviation, it's going to cover the area under the curve around 95.44%. But if you go both sides from the center, 3 standard deviation, it's going to cover the area under the graph or under the curve of normal distribution around 99.74%. Okay, so in this concept, the control chart is going to have the idea that, okay, if we develop the sampling distribution and we take the mean to be the center, then we're going to construct the control limit, upper and lower control limit. And that upper and lower control limit will construct based on using the number of standard deviation, right, from the center. So then if you have the mean here, you're using plus 3 standard deviation, we call it upper control limit. Minus 3 standard deviation, we call it lower control limit, something like that. So this is the concept that why we develop, right, the upper and lower using the number of the standard deviation. Generally, the popular one using 3. In some cases, we're using 2. But if you have no idea, using 3, the best one. But from the center as a mean, plus 3 standard deviation, this is upper control limit. Minus 3 standard deviation is the lower control limit, right? But this is the general one, right? So just like this, okay. And then we're gonna construct this control chart. This is upper control limit. This is lower control limit. This is a mean, right? And the control chart is a plotting of the average from the output of the process from time to time. Let's say this is an average output from the first one. This from the second hour, this from the third one, this from the fourth one, this from the fifth one. You're plotting the average, right? And then you calculate the average from every point, you have this one at the center. Plus 3 standard deviation, you have upper. Minus 3 standard deviation, you have the lower control. And the way that we evaluate is that we kind of look at, okay, if all the plotting points based on control chart stay within the control limit, we call process in control. If you have one or more outside the control limit, we call the process out of control. So why we do something like this? Because it is impossible that in the real world you're gonna make the sampling and develop the distribution every hour and see this one from time to time. We're gonna using just sampling just one time, calculate the average, right, and develop the control limit. If this one, not this one. Let's show you here. Yeah, okay, this one. You can see here. this is sampling number is mean the sample number from the first hour, the second hour, the third one, and the fourth one. Okay. Look here. This is just the average. Assume that this is the average weight of 5 boxes of cereal for the first hour. This is the average weight of 5 boxes of the second hour. This for the third one, this for the fourth one. And we develop the control limit. Okay, we have this one and this one. And we found that, okay, this potting point, the average one, stay within the control limit, right? We said it's in control. So we can imply that for every hour here, if we try to develop the sampling distribution, we're going to have normal the same every hour. So this is the reason why we use the control chart. Because we cannot, okay, spend time to develop the distribution for every hour and see it's the same distribution or not. We just, shortcut way, just make one sampling, right? And calculate the average one plotting. For the second hour, we sampling, calculate the average, another one plotting. We do plotting all the samplings, average one, and using the formula to calculate upper and lower, and see that the plot is within upper lower or not. If it stays within the control limit, okay, it's in control, which means that you can imply that if you want to construct the sampling distribution, you're going to have the same sampling distribution for every hour, just like this picture, just like this one. Okay, and this is the detail to explain you more. Don't worry, we not go into the calculation part yet, but I just tell you about the concept. So this is a control chart, okay? But you can see every plotting is for the average, right, from your sampling, right? Sample number represented for the first hour, from time to time, second hour, 3 hours, something like that. In this case, you can see if all the plotting points stay within the control limit, it means you have just normal or natural variation. But if you have one that outside, it means you have assignable or abnormal happen. But when we evaluate, we don't care that, okay, let's say that I'm plotting 15 points, 14 points stay in control limit, just 1 point out. We care that, okay, we have 1 point that out, so it's been all control. We don't care that, okay, first 14 is stay in control, just 1 is a little bit out. But in practical, it's our control. So all the plotting points need to be stay within the control limit, so then we call it in control. If just 1 point or more outside control limit, it's all out of control. Okay, and as I mentioned that we have several types of control chart. It depends on the type of the data. Generally, we have 2 types of the data. Data to be the variable data and data that we call the attribute data. Variable data is just like the data that's be the continuous value. So it's can be explained in the decimal point or fraction, something like that. So generally, we can think about if your data can be measured, right? Just like the dimension, weight, time, something like that. Strength, we call it variable data. But if you have the data that called attributes, means that the data is just like the classified two-way, categorized, right? We call it as discrete value. Good or bad, have the defect or not defect. Right? Can write or not can rewrite, something like that. Right? Break or doesn't break, something like that. So this one we call the attribute data, or the data that you can count in. Right? So for variable data, we're gonna have 2 charts, X bar and R chart, use it together. But for attribute data, we're gonna study C and P chart. So for this chapter, we study just for control chart. The calculation is very easy because there is no complex of the calculation. But the difficulty of the control chart is about which chart that you're going to apply to that process. Okay, so this is the key things. And how can you evaluate it? Okay, So this is an example. Once again, you can see wedge length, dimension, strength, time. This all the thing we call variable data. Attribute data is just like category one. You can count it the difference, like have defect or doesn't have the defect, something like good or bad, something like. Okay, and this one is just the concept that I just told you about the central limit theorem, that we are not study or apply from all the output that because we using the concept of sampling, right? Based on the concept of the central limit theorem, it states that if you make the sampling more enough, right? No matter what the population has any distribution, but the sampling distribution is gonna be the normal distribution, that you have the same mean with the mean of the process. And you can have the standard deviation of the sampling distribution equal to the standard deviation of the process divided by square root n. N is a sample size. Just like that, you sampling 5 boxes of cereal, so n is equal to 5, something like that. So this is the conclusion here. So if you look at this picture, you can see we have 3 pictures, right? Number A, B, and C, right? A, B, and C. The picture C is definitely out of control, right? Because output is out of the control limit, and the distribution doesn't the same. Picture B actually seems like it's in control because the distribution is quite the same, but it doesn't provide the output within the control limit or within the spec, right? So we don't want it, even though that you can expect the output is quite the same from time to time, but you have some of them that are the control limit or all the specification. But the figure A, right, this is the one that we want, because we have like all the outputs stay with the control limit, and the distribution of the sampling is quite the same from time to time, right? And this is the concept of central limit theorem that I just mentioned. The population is maybe beta distribution, normal, uniform, whatsoever. But if you make the sampling more enough, right, we can say that, okay, the sampling distribution is going to be normal. That has a mean equal to the mean of the process, mean equal to the mean of the population. And the standard deviation of the sampling equal to the standard deviation of the population or standard deviation of the process divided by square root n. Okay, and this one is nothing much. So this one is the same picture. Okay, before we go to the calculation part, you may see the more clearly about how can we develop the calculation and construct the control chart. We need to understand the order of control chart or the order of the SPC. Generally, we have 2 types of the order, type 1 and type 2, right? We're quite simple that the type 1 order is that actually is in the case that you conclude the process is out of the control, but actually is in the control, the type 1 order. Type 1 error is that you conclude the process is out of control, but actually that process is in control. But for type 2 error, you conclude the process in control, but actually is out of control. So it's different. Type 1 process is in control, but you make the conclusion that process is out. So generally we call the producer risk, right? Because actually you have the good result, but you make the conclusion is bad, so you don't use it, right? So you waste it. So it's producer risk. But for type 2 error, actually process is out of control, right? The output is not good, but you make the conclusion is good. Right? So then you deliver the output to the consumer. So it's called the consumer risk. Right? And this You may familiar with this one. Taiwan error stands from statcast, right? It's quite the same, right? From mean, this is normal distribution, right? The center is mean, right? You project 3 standard deviation, right? For both sides, you can have upper control limit and lower control limit. We know that the probabilities under the normal distribution is equal to 1, right? Is equal to 1, right? Area under this curve is equal to 1, represented for probability is equal to 1. So this area is the probability that you're going to have the Taiwan error. For type 2 error, I doesn't have the figure to show you because it's beyond our class, but just want you to know that the type 2 error is come from mean shift. But Taiwan is come from the probability that you have outside the control limit. Okay. And this one I already mentioned. Okay. So this is a step of creating the control chart. Actually, I already talked about this. I want to see this, so I'm going to start with this one. Let's start with the first control chart. The control chart for the wearable data. I told you that the wearable data is about the data that you can measure it, right? Just like the weight, speed, time, dimension, something like that. Yeah. It's continuous value. We're going to use X bar, not X bar chart and R chart. You have to use X bar chart and R chart together. Right. You cannot using one of them separately. You need to use all both these charts together. Because X bar chart, as its name states, X bar chart is used to measure or control the mean of the process. But for R chart, R is come from range. So R chart is used to control and measure the dispersion of the process. So we need to use these two charts together. And we're going to conclude that our process is in control. It's just in the case that both X bar chart and R chart are in control. Let's say that you measure the process, right? You have the X bar chart process in control. But for R chart, you have it out of control. We made the conclusion that overall is out of control. So if you go deeper, it means that if you have just only one point that out of the control limit from either of them, we make the conclusion is out of control. Right? Let's say that you're plotting the chart for X bar and R chart. If you have just only one point from these two charts out of the control limit, we make the conclusion that process is out of control. Okay. And please be careful about this because as I told you that the control chart for variable, we have X bar and R chart you need to use together. If the instruction of the exam said that, okay, you need to develop or construct the control chart for this data, blah, blah, blah. And that data, let's say, is about the weight. You know that you need to construct both control charts. Even though that you construct the first one and you found that, okay, it's out, but you need to develop both of them to show me, right? And this is a way that we're going to talk about the X bar chart first. Let's start with the X bar chart. Okay, so it's going to be very close to the statcast that you studied before. It depends that whether or not you know about the standardization of the population or the standardization of the process. So then I'm going to split into the two cases for the X bar chart. The first X bar chart is that in the case that you know the standard deviation of the process. Standardization of the process is for the standardization of the population. Yes, generally we don't know it, right? But maybe we can know if you have more enough historical data that you can estimate the standardization of the process. So the first case is that if you know about the standardization of the population or standardization of the process, so you know that the mean is about the average of all the plotting point, right? We call X double bar. The upper control limit, we're using X double bar plus number of standard deviation of the sampling distribution. For lower control limit, we minus. The Z is the number of standard deviation. Generally, we use 3. We use 3. And how about the standard deviation of this sampling distribution? Based on the concept of central limit theorem is equal to the standard deviation of the process or population, right? Divided by square root n. N is about the sample size, right? The number of output that you make samplings, right? From the process, right? So I will show you based on this example. Okay, let's say that we have the process of the production of objects, right, like the boxes. And just for sure, just the same as the first example, that we may concern about the weight for every boxes of the 4 things. So then at hour number 1, the first hour, I'm going to the production line at the output of the process, and then I make the sampling 9 boxes of object, and I measure the weight of that 9 boxes. So this is the weight of the box, right? On 17 on, 13 on, 16 on, something like that. And then I do average from all the 9 boxes. I have average is 16.1. For the second hour, we do the same things, right? We make the sampling 9 boxes of object, measure the weight from all of them, average the weight from 9 boxes. I have 16.8. The third hour, I make the sampling 9 boxes again, measure the weight for each of them, calculate the average weight. I have 15.5. I'm do the same way. Let's say I'm do 12 hours. So this is the value of the mean of 9 boxes for every hour. Okay. Let's suppose that we know about the standardization of the population or standardization of the process. From the historical data, we have is equal to 1. So then we know that this is about the weight. Weight is about the variable data. So I'm gonna develop the X bar chart. So we know that the central one, X double bar, is come from what? From the average of plotting point, right? So I use 16.1 plus 16.8 plus 15.5 plus 16.5 until plus the last one 17.3, all divided by 12. I'm going to have X double bar. Let's say X double bar is 16. And then based on X double bar is 16, I'm using number of standard deviation equal to 3. So then I'll calculate the upper quantum limit by using the X double bar plus 3 standard deviation, remember? So X double bar is 16, C is 3, but the standard deviation of sampling distribution based on the concept of central limit theorem is equal to what? Standard deviation of population divided by square root n, right? So in this case, we know that standard deviation of sampling distribution equal to the standard deviation of process divided by square root n. So then you have 1 divided by square root 9. So that's why you have 1 over 3, this one. So then you can have upper quantum limit X double bar plus 3 multiplied with 1 over 3. 1 over 3 is come from that one. I just show you. And it's equal to 17 ohms. And for the lower control limit, right, using X double bar minus Z standard deviation of sampling distribution. So then we have minus 3 multiplied with 1 over 3. So we have 15 ohms. Okay. And then you plot the graph. You can see this is 16.1, remember? This one from the first hour 16.1, this is 16.8, this one 15.5 from the third one, 16.5, something like that. You're plotting 12 point, right? The mean is X double bar 16. Upper quantum limit, that's you just calculate 17. Lower quantum limit 15. And then when you look at this, you have this 3 point out of the control limit. So we make the conclusion this process out of the control. And what we can evaluate more from here, we can see that okay, this is out of control because we have the point that out of the control limit. And if we go more detail here, we can see that since hour number 10, the point is out of the control limit. So something wrong since hour number 10. You might investigate more at hour number 10 who perform the operation, right? Which labor or worker that doing this operation, how they do it, right? What kind of procedure that they follow? Do they calibrate their machine or not? Or do they doing something wrong that different from other hours, something like that? You will see something that different from other hours. So then we try to correct it, and then we develop the new control chart to see that whether or not the process in control, right? So this is quite a step. So you can see that the calculation is not that difficult, and this case is not that it's like a rare case because generally in the real world we have no idea about the standardization of the process. Right. So then we can have another formula, which means in the case that you don't know about the standardization of the population or standardization of the process, how can we develop the control chart for X bar chart against the mean of the control chart is X double bar that calculate from the average from all the points that we're plotting. Upper control limit, then this time we use X double bar plus A2 R bar. Lower control limit, we're using X double bar minus A2 R bar. What is A2 and R bar? Okay, let's see A2. This is just like the standard factor that they have someone that developed already. Right? We're gonna use this value. Actually, we're gonna have like a table. The value of A2 is depend on sample size. If you make the sampling 5 boxes, you're using A2 0.577. If you make the sampling 9 boxes, let's say, you can use the number value A2 0.337. Okay, it depends on N. Don't see this one. It's just okay. Just look at A2, right? And how about R bar? How about R bar? R is come from range, right? From range. So here the detail. I don't have any calculation to show you, so you need to listen to me. Back to this example, okay? For the first hour, we make the sampling 9 boxes, right? And this is the weight for of that 9 boxes. We have the average one, 16.1. R is come from range. Range is calculated from maximum minus the minimum. So in this case, for the first hour, the maximum weight based on 9 boxes that we make the sampling is 18. The minimum weight is 13. So the range of the weight based on the first hour is 18 minus 13. We have 5. 5 is R1, right? We call it R1 because this is for the first hour. So it means for the second hour, we're going to have the detail for 9 boxes, right? We're going to have the maximum weight and you're going to have the minimum weight. You find the difference, you have R2. Okay? So then if you have 12 hours, you're going to have R3, R4, R5, R6 until R12. R bar is what? Is the average of all R1 until R12. You're using R1 plus R2 plus R3 until plus R12 and all divided by 12. That is the R bar. Okay. So this one we're going to use a lot because it's more practical. Since in the real world, maybe we don't know about the standardization of the population. So that we can apply this formula to upper and lower control. And this is not the same This is not the same example. Okay, I'm just showing you about how can we substitute the value from the table. This is not the same example. Right? Let's say that I calculate x of y is 16.01, r y is 0.25, and it's 5, right? And it's equal to 5. We go to the table, and it's 5, a2 is 0.577. So then, we're gonna have this one, right? X bar 16.01 plus a2 0.577 multiplied with r bar 0.25. So then you have 16.154. For this one, right? You substitute minus, so you can have 15.866. Just show you about how you substitute the value from the table. Not the same example as previous one. How about the next one? Oh no, sorry. If I try to do a control chart, I can have the mean, right? X double bar, this is upper, this is lower, okay? How about the next one, R chart? You can see something, right? X bar chart, reporting what? Reporting average weight, right? Based on that example. X bar chart reporting the average value. How about R chart? R is come from where? Can you guess this? R chart, we're gonna plotting range. Remember the way that I'm showing you how can we calculate R bar? The first hour we have R1, the second hour we have R2, right? So that range is the point that we're gonna plotting for R chart. Okay. R chart is range chart, so we're plotting the range. X bar chart is an average one, right? We're plotting the average value. So we're plotting the range, right? And we also have two formula as well. No, the popular one is this one. This is the case that you don't know about the standardization of process or standardization of population. So then the mean is R bar. Mean is R bar. Upper control limit, you're using D4 multiplied with R bar. Lower control limit, you're using D3 multiplied with R bar. What are they? D3 and D4 is come from the same table as A2, D3 and D4. It depends on the number of sample size. Okay, so for R chart, the mean is R bar. Upper control limit, you're using D4 multiplied with R bar. Lower control limit, you're using D3 multiplied with R bar. Right, and then you plotting R. How about the case that you know about the standardization of process or standardization of population, sigma, that one? We can use upper and lower from this formula. Okay. So, let's say here, suppose that I calculate R bar is equal to 5.3. We make the sampling n equal to 5. So based on the table, if n equal to 5, D4 will be equal to 2.115. D3 going to be 0, right? So then we substitute D4 2.5, 2.115 multiplied with R bar. Then we have 11.2. But for D3 0, you have 0. So then when we plot, the mean is 5.3. This is R bar. Upper is 11.2. Lower is 0. And then you plotting R. Okay. So this is the X bar and R chart. Not difficult, but very easy. And this is the slide to show you that why we need to, using both of them together. Why we need to use both of them together. Because, look at this one. If we look at this distribution, let's say this distribution from the first hour, this is from the second hour, this is from the third one, this is from the fourth one. If you look at the graph here, same distribution, right? Same share distribution. So if you use just only, R chart to measure,
when you plotting, you're gonna have in control because all the plotting points stay with the control bit, right? Because we have the same shape and this version is quite the same. So that's why R chart is show in control. You might have the mistake. Because if you're using X bar chart to measure this process, you're gonna see that when you're plotting, the value is out of control. Because in this case, the mean is doesn't the same. Right? It's gonna detect by X bar chart, not R chart. But for this case, if you have this case, mean is the same, but you have the difference of this version of the base of the distribution. If you're using X bar, it shows in control for sure because mean is quite the same. But it can detect that this process out of control by using R chart because the dispersion is not the same. So that's why for the variable data, we need to apply both X bar and R chart together because the one X bar chart measure about the mean. The second one, R chart, measure about the dispersion. We need to apply it together. And we will make the conclusion that the process in control in the case that both R chart and X bar chart are in control. Okay. And this is the example of the real one. It's plotting R chart and X bar chart together. Right? You can see that this is like the control limit. This is the mean. Like control limit, this is about the mean, this for X bar chart, this for R chart. Generally that if you have the program, right, software program, when you're doing like the operation outside, sometimes we have the software to calculate and solve the control chart for us. It's gonna plotting same time, right, showing that both of these two charts together, right? So in this case, you can see that it needs to be used together. Okay, and for X bar and R, it's not that the problem much because it's quite obvious that if you have the data just like weight, dimension, length, time, speed, strength, is for sure that it's continuous value. You're going to use X bar and R chart together. But the problem when you're doing the exam is come from the attribute data. Because the attribute data, the data is like the categorical data, right? Good or bad, defect or doesn't have defect, some data. Or we can say that the data that can be counted. Right? We have two charts to measure all the data, right, of this attribute data. We have P chart and C chart. P chart and C chart. The problem is that sometimes you confuse about P chart and C chart. P chart is using for P, using for the proportion or the fraction of defective product in the process. But for C chart, we use for the number of defect product per unit. It's different. Because P chart is proportion, P comes from proportion. So when you do like the P chart, it means that we plotting the proportion of defective product of the process. And let's say that, okay, again, I'm using the same examples as last week. We have the pen, right? These two pens come from the same process, same production line, and make the sampling at the same time. If this one can be ripened, this cannot be ripened, so they have some defect, right? If I make the sampling just 5 pens, it probably defective product percentage is maybe 0, right? Because generally you can see the fraction or the proportion of defective product in the case that you make enough of sampling size. So then generally for P chart, when you're gonna have the sampling, we can use like the 50, 100, 200 or 300 because it can show about the fraction of defective product in the process. If you make the sampling just like 5, 9, Probably, for sure, let's say that this process, I'm sampling 5 pen and try to use it to write, it can write all of them. Almost 99.99% for sure. But if I'm making the sampling, let's say 500 pen, it might be 1 or 2 that have the problem. So that I can measure about the fraction of defective product. So my point is that when you use a P chart, you need to make the sampling of the output of the process big enough. Normally it's 50 or more, right? 100, 200, 300, something like that. And for C chart is, since I said that it's measure about the number of defective product per unit. So it means that you need to have what kind of unit that you measure, right? Per unit, right? For example, you make the customer complaint per day, unit is day. You make the measurement of number of bacteria per unit of volume per liter, something like that. You make the number of scratch per item. You make the number of crack per one for 10 centimeters, something like that. You need to have the unit. Right? What kind of per unit? What kind of unit you're going to use? Right? Okay, and again, you can notice from its name. Let's start with P chart. Okay, P chart. P is come from proportion. We all know that X bar chart reporting mean, reporting average value. R chart reporting rate, right? So P chart reporting proportion. And P bar is going to be the mean of the control chart for this P chart. P bar is like the average of the proportion. Right? And upper control mean we're using P bar plus Z multiplied with standard deviation or sigma or P hat. So P hat is calculated from using formula. Right? Using square root of P bar multiplied with 1 minus P bar all divided by N. N is the sample size. For the lower control mean we're using P bar minus Z multiplied with standard deviation of P hat. We have been using this formula. And Z normally we're using 3. We're using 3. 3 standard deviation. Right? So, for example, in this case, let's say that, okay, I'm not sure what kind of process we have. Let's say that I make the sampling, right, 100 units for the first hour. It has 6 units that have the error. So the fraction of defective product for the first hour is 6 over 100. So then they have 0.06. For the second hour, the second sample, I make the sampling 100 units. Just 5 of them have the defect. So the fraction for the second hour is 5 over 100. We have 0.05. For the third hour, I make the sampling 100 again. There is no defect. So the fraction is 0. Okay. If I do something like this for 20 hours, I'm going to have 20 point of fraction of defective product. Right? This is the one that we're going to plot in. This is the one that we're going to plot. The fraction of defective product. How about the mean? P bar. P bar you can calculate 2 ways. Right? It's actually the same. But the first way is that you're using the fraction that you're going to plot for every hour, sum together, divided by 20. 0.06 plus 0.05 plus 0 plus 0.01 plus 0.04 blah 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 until you plus 0.04 all divided by 20. You can have P bar. That would be equal to 0.04. Or you can calculate based on this one. Every time that you make the sampling, you make 100 units. You make the sampling for 20 hours, right? So the total number that you make sampling is 20 multiplied with 100. And you counting number of error. You have total error is 80. So then you're using 80 divided by total number that you sampling. So you have P bar equal to 0.04. It's the same. Okay. So for me, normally we prefer another way. I prefer the way that we're using all this, sum together divided by the number, find the average one. And how about standard additional p hat? You make the square root, right? This is p bar. P bar multiply with 1 minus p bar. So we have 0.04 multiplied with 1 minus 0.04 divided by n. N is the sample size is the 100. And then we take the square root, we have 0.02. So then from here, what do we have is upper control limit is p bar plus z. So we're using 3, right? Standard of p hat, we have 0.02. So we have 0.04 plus 3 multiplied with 0.02, we have 0.1. And you look carefully here for lower control limit. We use 0.04 minus 3 multiplied with 0.02. Actually, we should have negative value, right? But for control chart, we don't have negative for lower control limit. If you have the negative value for lower control limit, we using 0 instead. So in this case, actually we should have minus 0.02, right? But we don't use it. We can use 0. Right? For lower control limit, there is no negative value. If you calculate getting the negative one using 0. So then you have lower control limit 0, upper control limit 0.1. The mean of p bar is 0.04. You plotting the fraction, right? This is the value that you plotting from here. 0.06, 0.05, 0, 0.01, 0.4, something like that. This one. Right? 0.06, 0.05, 0, 0.01, something like that. And this one is what? Is the control limit, right? So we made the conclusion that this process is out of control, right? Because we have one point that's out of the control limit. Okay, so this is the P chart. Okay, so we have the practice problem, right? Another sheet, right? I give you. So we're gonna see that one. So this is just a theory. Okay, so this is for P chart. Okay. We will have another one is C chart. C chart. Let's say C chart, and then we're gonna have the break, right, for your dinner. C chart is, you're gonna plotting number of defective product per unit. So the mean is C bar. C bar is the number of defective product, the mean of them. Upper control limit is using C bar plus 3 multiplied square root of C bar. Lower limit is C bar minus 3 multiplied square root of C bar, right? The example is not that, in the slide is not that clear, but you need to listen to me for my explanation. Okay. In this case, we try to measure about the process of customer complaint of the cab company. Okay. For the first day, right, we have the complaint equal to 3, right, based on the public. This is number of complaint per day. The first day, 3 complaint. Second day, we have no complaint. The day number 3, we have 8. Day number 4, we have 9, something like that. Let's say that we measure 9 days. Total complaint is 54. 54 based on 9 days. So the mean is 54 divided by 9. We have 6 complaints. Right? Why we're using C chart? Because it's this complaint per day. We have 6 complaints. And then upper complaint, we have 6 plus 3 multiplied square root 6. We have 13.35. How about the lower? This one is typo, right? For the lower complaint, this one 6. Change this one to 6. 6 minus 3 multiplied with square root 6, you should have negative value, right? But then we're using 0. So then we're plotting, right? And there is no point that out of the control limit. So in this case, process is in control. But this example, we're using C chart because we measure about the complaint per day. If you want to use P chart, it's gonna be like this. For the first day, we sampling 100 customer and how many customer complain for that 100 customer. Right? You can have like a fraction that means the whole thing. For the day number 2, you make a sampling 100 customer and ask them how many of, and ask them and make sure that how many of them they complain based on 100. Right? So it's like that you need to make the sampling first, right? And see the fraction. That would be the P chart. But for this case, C chart, we don't care because our unit is per day. Right? We're counting all of them for 1 day. We have 3, we have 0, we have 7, we have 8, something like that. But for P chart, you need to make the sampling. Right? Make a sampling, 50 customers, how many of them complain? Let's say 2 of them. So the fraction is 2 over 50. That would be the fraction for the first hour, something like that. Okay. We're going to talk about this later, right, for the calculation example. So, in conclusion, for the control chart, you need to make sure that you're using the right type of the control chart for the type of data, variable or attribute. The sample size is quite important. So make sure that you're using the one that appropriate for your process. Right. And which point or what point in the process that you're gonna use in the control chart. Normally it's gonna be very simply or the important. So then you use the control chart to make sure. Right? Okay. So this is just the overall of 4 control chart. Right? We're gonna see the example later. Okay. So now we're gonna have the break. Okay, for having dinner. And then we're gonna back to see the rest of the information and do the example. Okay.